Engineering Chemistry, Module 1, Electrochemistry and Corrosion. Part 1 of Module 1 deals with the following topics: Introduction, differences between galvanic cell and electrolytic cell, Daniell cell, salt bridge, electrode potential, Helmholtz electrical double layer, types of electrodes, reference electrodes, glass electrode, and potentiometric titration. Electrochemistry is a branch dealing with two types of energy conversions. Either chemical reactions can be produced by passing current through an electrolyte, or we can produce current from various chemical reactions. Thus, based on these two types of energy transitions, we have two types of cell. One is electrochemical cell, which convert chemical energy into electrical energy, and the second one is electrolytic cell, which convert electrical energy into chemical energy. So, what are the differences between a galvanic cell and an electrolytic cell? The main difference lies in the type of energy conversion, as we said earlier, where a galvanic cell, it converts chemical energy into electrical energy. Here, the anode is negative and cathode is positive, and it gives a spontaneous redox reactions. Also, it does not require any external voltage source. In the case of electrolytic cell, it converts electrical energy into chemical reactions, and here the anode is positive and cathode is negative, and it gives a non-spontaneous reactions, and also it requires an external voltage source. Daniell cell is a simple example for a galvanic cell. It consists of a zinc rod dipped in zinc sulfate solution, which act as anode, and a copper rod dipped in copper sulfate solution, which act as cathode. The electrode reactions are anode, where an oxidation reaction takes place, so zinc, it gets oxidized to zinc 2 plus, and the cathode, where a reduction reaction takes place, where Cu2 plus, it gets reduced to Cu. So the overall cell reaction is zinc plus Cu2 plus, it gives zinc 2 plus and Cu. What is a salt bridge and why it is used in an electrochemical cell? Salt bridge, it is an inverted U-tube and it provides a continuity of electrical circuit. It also prevents interfering ions diffusion and helps to maintain electrical neutrality and eliminate liquid junction potential. Common examples of inert electrolyte which is used inside the salt bridge are potassium chloride, ammonium nitrate, etc. The term electrode potential defines as the tendency of electrode to lose or gain electrons when it is in contact with its own ionic solution. Electrode potential is divided into two. One is known as oxidation potential, which is the tendency of electrode to lose electrons when it comes in contact with its own ionic solution, and the second one is reduction potential, which is the tendency of electrode to gain electrons when it is in contact with its own ionic solution. We have seen that anode is negative and cathode is positive in an electrochemical cell. This concept, it can be explained on the basis of the formation of Helmholtz electrical double layer. When a metal electrode is placed in contact with its own ionic solution, like a metal M is placed in a solution containing Mn plus ions, either it can undergo an oxidation reaction or it can undergo a reduction reaction. During oxidation, metal ions enter into the electrolyte, leaving behind electrons on the electrode surface itself. Because of the presence of these negatively charged electrons, anode gets a negative charge. This negatively charged anode starts attracting positive ions from the solution to form a double layer of charges known as Helmholtz electrical double layer. Likewise, during a reduction process, positive metal ions from the solution takes electrons from the electrode and gets deposits as metal. Thus, cathode gets a positive charge and starts attracting negative charges from the solution to form Helmholtz electrical double layer. There are different types of electrode. One of the type is metal-metal ion electrode. When a metal is immersed in its respective metal salt solution, it forms metal-metal ion electrode. For example, when you place a zinc electrode in zinc sulfate solution or a silver electrode in a silver nitrate solution or a copper electrode in a copper sulfate solution, they all forms a metal ion electrode. The general representation which is used for these type of electrode, for oxidation it is M/Mn plus, and for reduction it is Mn plus/M. For example, if we consider the oxidation reaction of zinc, like zinc giving zinc 2 plus 2 electron, the representation is zinc/zinc 2 plus. And for the reduction reactions of copper, like Cu2 plus 2 electron giving Cu, the representation used is Cu2 plus/Cu. The second type of electrode is gas ion electrode. In this type, the gases pass through an inert electrode like platinum, which is immersed in a solution containing its own ions. For example, in the case of hydrogen electrode, hydrogen gas is bubbled through the platinum electrode immersed in HCl solution, or in the case of chlorine electrode, chlorine gas is bubbled through platinum electrode immersed in NaCl solution. The general representation used for gas electrode is, for oxidation it is platinum/X2/X minus or plus. Here X2 denotes the gas, X minus or plus it denotes the ions present in the solution. For reduction it is X minus or plus/X2/platinum. For example, if we consider the oxidation reaction of hydrogen, like H2 giving 2H plus 2 electron, the representation is platinum/H2/H plus. And if we consider the reduction reaction of chlorine, like Cl2 plus 2 electron giving 2Cl minus, the representation is Cl minus/Cl2/platinum. Another type of electrode is metal insoluble metal salt common ion electrode. In this type of electrode, the metal is covered with a paste of its insoluble metal salt, which is in contact with a solution containing a common ion with the insoluble salt. For example, calomel electrode. In this type of electrode, mercury is in contact with an insoluble precipitate Hg2Cl2, which is in contact with KCl solution. Another example is silver chloride electrode, where silver is in contact with the precipitate of AgCl, which is in contact with KCl solution. The general representation for this type of electrode is, for oxidation it is M/Mx/X minus, where M is a metal, Mx is an insoluble metal salt, and X minus is a common ion. For reduction, the representation is X minus/Mx/M. For example, if we consider the oxidation reaction of calomel electrode, Hg2Cl2 plus 2 electron giving 2Hg plus 2Cl minus, the representation is Hg/Hg2Cl2/Cl minus. And if we consider the reduction reaction of calomel electrode, like 2Hg plus 2Cl minus giving Hg2Cl2 plus 2 electron, the representation is Cl minus/Hg2Cl2/Hg. Another type of electrode is a redox electrode. In this type of electrode, an inert electrode like platinum is in contact with a redox system. For example, when a platinum electrode is immersed in a mixture of ferric chloride and ferrous chloride solution, that is Fe2 plus and Fe3 plus solution, or a platinum electrode is dipped in a mixture of ceric sulfate and cerous sulfate, that is cerium 4 plus and cerium 3 plus solution. The general representation used for redox electrode is, for oxidation it is platinum/Mn1 plus semicolon Mn2 plus, where Mn1 plus denotes the ion with lower oxidation state and Mn2 plus it denotes the ion with higher oxidation state. For reduction, the general representation is Mn2 plus semicolon Mn1 plus / platinum. For example, if we consider the oxidation reaction of Fe2 plus giving Fe3 plus electron, the representation is platinum/Fe2 plus semicolon Fe3 plus, And if we consider the reduction reaction of Fe3+, that is Fe3 plus electron giving Fe2+, the representation is Fe3 semicolon Fe2 /platinum. Last type of electrode is metal amalgam electrode. In this type, a metal amalgam is dipped in the solution of metal ion. For example, lead amalgam, when it is kept in contact with Pb2+ ion, it forms a metal amalgam electrode. The general representation used here is, for oxidation it is MHD/Mn+, where MHD denotes the metal amalgam and Mn+ denotes the metal ion. For reduction reaction, the representation is Mn+/MHD. For example, if we consider the oxidation reaction of lead, Pb giving Pb2+ plus 2 electron, the representation is Pb of Hg/Pb2+. And for the reduction reaction of lead, like Pb2+ plus 2 electron giving lead, the representation is Pb2+/Pb of Hg. The next topic is about the reference electrodes. Reference electrodes are those whose potential is already known, and this can be used to find the potential of other electrodes. Standard hydrogen electrode, or SHE, is known as a primary reference electron, and this is an example for a gas type of electrode. The apparatus consists of an inert platinum electrode dipped in 1 molar HCl solutions. This platinum electrode, it is coated with platinum black and helps to attain the equilibrium between hydrogen gas and H+ ion. This is surrounded by a coaxial tube which has a small opening to pass hydrogen gas at 1 atmosphere. The potential of standard hydrogen electrode is taken as 0. Depending on the potential of coupled electrode, SHE can act as either anode or cathode. If the potential of coupled electrode is less than 0, then SHE will act like cathode and undergoes a reduction reaction 2H plus 2 electron giving H2. And if the potential of coupled electrode is greater than 0, then SHE will act like anode and undergoes an oxidation reaction H2 giving 2H plus 2 electrons. Standard hydrogen electrode, it can be used to find the single electrode potential of other electrodes. For example, if we want to find the electrode potential value of copper, we couple the copper electrode with the primary reference electrode, standard hydrogen electrode. Here the standard hydrogen electrode will be acting like anode and the copper electrode will be acting like cathode. So E cell is equal to E cathode minus E anode, where E cathode is the copper electrode and E anode is the standard hydrogen electrode whose potential is taken as 0. So the potential of copper electrode is equal to E cell plus 0, where the E cell value we can obtain from the voltmeter reading. There are certain limitations for SHE, and some of them are: it requires a considerable amount of test solution to conduct the experiment. The electrode can be easily poisoned by the presence of mercuric, arsenic, sulfur, etc. SHE, it cannot be used in a solution containing a redox system, and it is very difficult to maintain a pressure at 1 atmosphere. Also, the apparatus, it is very costly due to platinum. Due to the limitations of primary reference electrode SHE, we use another electrode, calomel electrode. The calomel electrode is known as a secondary reference electrode and is an example for metal sparingly soluble salt anion electrode. The apparatus consists of a long glass tube. At the bottom, there is a small amount of mercury. This is covered with a paste of solid mercurous chloride, which is further in contact with a solution of KCl. And there is a platinum wire dipped in mercury layer for making the electrical contact. The side tube present in calomel electrode itself act like a salt bridge. The potential of the calomel electrode varies with the concentration of KCl solution, and it is given in the table here. And we can see that if we use a decinormal solution of KCl, that is 0.1, calomel electrode has a potential 0.3335 volt. And if we use a normal solution of KCl, that is 1 normal, the electrode potential of calomel is 0.2810. And if we use a saturated KCl solution, the electrode potential of calomel is 0.2422. And we generally used a saturated calomel electrode for the experiments. Depending on the potential of coupled electrode, calomel electrode can either act like anode or cathode. If the potential of coupled electrode is less than calomel, then calomel electrode will be acting like cathode and undergoes a reduction reaction. Hg2Cl2 plus 2 electron gives 2Hg plus 2Cl minus. And if the potential of the coupled electrode is greater than calomel, then the calomel electrode will be acting like anode and undergoes an oxidation reaction. 2Hg plus 2Cl minus gives Hg2Cl2 plus 2 electron. In order to measure the standard electrode potential of zinc, the zinc electrode is coupled with the reference electrode, calomel electrode. Here, the zinc will be acting like anode and undergoes oxidation reaction, and the saturated calomel electrode will be acting like cathode and undergoes the reduction reaction. So the E cell is equal to E cathode minus E anode, where E cathode is the saturated calomel electrode and has a potential value 0.2422, and E anode is the zinc electrode. So the potential of zinc electrode is equal to E cell plus 0.2422, where E cell value we obtained from the voltmeter. Next, we deal with an ion selective type of electrode, glass electrode. Glass electrode consists of a low melting gas with good conductivity. It consists of a long glass tube with a glass bulb at the bottom. It is filled with 0.1 normal HCl solution, and there is a silver wire coated with AgCl for the electrical contact. Here, the glass membrane acts like an ion exchange resin and set up an equilibrium between Na plus ions of glass and H plus ions of the solution. Since the concentration of H plus ions inside the glass remains constant, when it is dipped in a solution of unknown pH, it becomes sensitive to the outside H plus ion concentration and develops the corresponding potential. Thus, the potential developed by the glass electrode Eg is equal to E naught G minus 0.0591 pH, where E naught G is a constant for a particular variety of glass. In order to find the pH of unknown solution using glass electrode, the glass electrode is dipped in the solution of unknown pH and is then coupled with the reference electrode, saturated calomel electrode. The cell representation of this cell setup is Ag/AgCl /0.1 molar H plus /glass /H plus of unknown solution, salt bridge, KCl /Hg2Cl2 /Hg. As we said earlier, here the glass membrane will set up an equilibrium between Na plus ions of glass and H plus of the solution. So E cell is equal to E cathode minus E anode, where E cathode is a reference electrode, saturated calomel electrode, and has a potential value 0.2422, and E anode is a potential developed by the glass electrode and is given by E naught G minus 0.0591 pH. Thus, pH of the unknown solution is given by the equation E cell minus 0.2422 plus E0G, the whole divided by 0.0591. Some of the advantages of the glass electrodes are, it can be used to find the pH of both oxidizing and reducing agents, and even colored solutions can be used. The apparatus, it is not easily poisoned, and this can be used to determine the pH of solutions up to 10. Also, the apparatus is very simple to operate. Some of the disadvantages are the glass membrane used in the electrode is having an appreciable resistance. We have to use special electronic potentiometer. Glass electrode cannot be used to determine the pH of solutions above 12. It cannot be used in solutions containing ethyl alcohol, gelatin, etc. A very important application of EMF measurement lies in potentiometric titration. The basic principle behind the potentiometric titration is that the potential of an electrode depends upon the concentration of a specific ion to which it is reversible in accordance with the Nernst equation. To conduct a potentiometric titration, we require two electrodes. One is indicator electrode, whose potential keeps on changing with the concentration of specific reactant. Second one is the reference electrode, whose potential remains constant. In order to determine the end point of the titration, we note the change in electrode potential upon the addition of a titrant. And at the end point, there will be a large change in the potential value in accordance with the large change in the concentration of specific ion. Redox potentiometric titrations are titrations involving redox reaction. For example, we consider the redox reaction between Fe2 plus and cerium 4 plus ions. So in the beaker, we took Fe2 plus solution and we dipped the inert electrode platinum and the reference electrode saturated calomel electrode in Fe2 plus solution. The oxidizing agent cerium 4 plus is added from the burette so that it oxidizes Fe2 plus to Fe3 plus ion and set up a redox electrode platinum / Fe2 plus semicolon Fe3 plus. Here, the titration involves the transfer of electrons from the substance being oxidized to the substance being reduced. Here we can see that the reduction potential value of cerium 4 plus is more than Fe3 plus. So cerium 4 plus is capable of oxidizing Fe2 plus to Fe3 plus. The redox reaction is given by cerium 4 plus Fe2 plus gives cerium 3 plus Fe3 plus. The procedure for the experiment is cerium solution is taken in the burette and is added to the acidified ferrous sulfate solution taken in the beaker. Here we note the EMF reading for each addition of cerium 4 plus. As the titration proceeds, the concentration of Fe3 plus increases since cerium 4 plus oxidizes Fe2 plus to Fe3 plus and hence a redox system is established, and so the potential of the indicator electrode gradually increases. At the end point, there is a sharp increase in the potential value as no more Fe2 plus is available for oxidation. In order to determine the end point of the potentiometric titration, we plot two graphs. The first graph is between EMF and volume of cerium 4 plus, and the second graph is between delta E by delta V versus volume of cerium 4 plus. In both the graph, the maximum change of potential is taken as the end point for the potentiometric titration. Some of the advantages of the potentiometric titrations are the apparatus is very simple, cheap and reliable. This can be used in color liquid, solutions containing mixture of solutes and even in precipitation titrations. Thank you.